We can only get so far in our understanding of the properties of solids by thinking about ionic bonding. So to really understand many of the properties we're going to encounter later on, we need to understand covalent bonding. To build up to that understanding of covalent bonding, we're going to have a couple of lectures that will be probably review for some of you, especially if you're a chemistry major. In this lecture, we're going to talk about the basic properties of atomic orbitals. The whole revolution of quantum mechanics and Schrodinger's wave mechanics is that we treat the electron like a wave. If we write the wave function in spherical polar coordinates, we can break it into a radial part, which describes how the wave function changes as we move away from the nucleus in any direction. And then we have an angular part, which describes the wave function in terms of the variables theta, which is the deviation from the z-axis here, and phi, which is the angle in the xy plane. Now, as you probably know, every electron has 4 quantum numbers that specify its behavior. So we have a principal quantum number, n, which takes integer values starting with 1, and that's going to describe the size of the orbital and also its energy. In a 1-electron atom, like the hydrogen atom, the principal quantum number alone specifies the energy. Then we have the orbital angular momentum quantum number, sometimes called the Azimuthal quantum number, and this is going to define the shape of the orbital. So as we'll see on a slide or two, the value of the orbital angular momentum quantum number tells you if you are in an s orbital or a p orbital or a d orbital. The allowed values of this quantum number range from 0 up to n-1, where n is the principal quantum number. And in a multi-electron atom, both the principal quantum number and the orbital angular momentum quantum number determine the energy of that orbital. Then we have the magnetic quantum number, m sub l, and that can take values from -L to +L. It defines the orientation of the orbital. And finally, we have the spin quantum number, which has 2 allowed values, +1/2 and -1/2. And that defines the spin of an electron, which is a purely quantum mechanical principle, but definitely has important implications, particularly when we get to magnetism. Let's take just a quick minute and review some of the basics of quantum mechanics and atomic orbitals. So remember, the Pauli exclusion principle tells us that no 2 electrons can have the same set of quantum numbers. And what this means is each orbital can hold 2 electrons, one with the spin quantum number +1/2 and one with the spin quantum number -1/2. There's also Hund's rules, and here we're just going to deal with Hund's first rule, which tells us that if we have degenerate orbitals that are at the same energy, like for example when we might encounter the d orbitals, we'll see there's 5 degenerate orbitals, and Hund's rule tells us that the lowest energy configuration is the one that maximizes the electron spin. So that tells us that we want to put electrons all with the same spin, and because of the Pauli exclusion principle, then it says we want to put those electrons in different orbitals. And the rationale behind Hund's first rule is that because the electrons repel each other, if we keep them with the same spin, that will minimize the interaction between electrons and hence their repulsion. And then an important thing to talk about are nodes. So a node is a place where the value of the wave function goes to 0. And it goes to 0 because the sign of the wave function is changing from positive to negative or vice versa. In a minute, we're going to talk about the probability density of an electron in an orbital, and that goes to 0 at a node. And we'll see that we have 2 kinds of nodes. Radial nodes, where the radial part of the wave function goes to 0, and nodal planes, where the angular part of the wave function goes to 0. All right, let's start with the s orbitals. Because the s orbital is spherical, it means that the angular part of the wave function is just a constant. So really, we learn everything we need to know about the wave function by looking at the radial part of the wave function. And what's plotted here in the upper part of this slide are the wave functions for the 1s, 2s, and 3s hydrogen orbitals. All of them have a peak at the nucleus. That's where the wave function reaches its maximum value, and then it drops away as we move away from the nucleus. For the 1s orbital, the wave function is always positive. There's no change in sign of the wave function. There's no node for the 1s orbital. For the 2s orbital, we see that at a value here of about an angstrom, the wave function goes from positive to negative. Right? So think about this like ripples in a pond. There's a positive part of the wave function where the height of the wave is above the level, undisturbed pond. And then there's a trough, or a negative part of the wave function, where the height of the wave goes below the height of the undisturbed pond. And so there's a crossover between those two at about 1 angstrom, and we call that a radial node. And then for the 3s orbital, we see that the wave function starts positive at the nucleus, then becomes negative when it goes through this node, and then it has yet another node at a further distance where it becomes positive again. So the 3s orbital has 2 radial nodes. And in fact, the number of radial nodes is equal to the principal quantum number minus the orbital angular momentum quantum number minus 1. So these are s orbitals. L, the orbital angular momentum quantum number, is 0. And so we see the 1s orbital has no nodes, the 2s orbital has 1 radial node, and the 3s orbital has 2 radial nodes. The figures below show what's called the radial probability function. In that function, what we're going to do is we're going to square the value of the wave function, and then we're going to multiply that by 4 pi r squared, which is the area of the surface of a sphere. And that gives us the probability of finding an electron at that point in space. Now, the maximum is not at the nucleus, because of course at the nucleus, the area of a sphere is 0. So as we move outward from the nucleus, we see that there is a maximum in the radial probability function at about 0.54 angstroms for the 1s orbital and a hydrogen atom. For the 2s orbital, we have a small peak here, not too far from the nucleus. Then we have a node, and then we have a larger peak out here. So we can see that most of the electron density now has moved out further from the nucleus, and we have 1 radial node. And then for the 3s orbital, we see that we have 2 radial nodes, and we have 2 sort of smaller peaks in the radial probability function. And then we have, the maximum in the radial probability function, which is happening out here at something like 7 angstroms. So quite a bit further from the nucleus than we had with the 1s orbital wave function. So here we see that as the value of n increases, the size of the orbital also increases. Now, not all of the orbitals are s orbitals. When you go to p orbital, that means the value of L is 1, and there is a plane that cuts through the orbital where the value of the wave function goes to 0. We call that a nodal plane. So a p orbital has 1 nodal plane and therefore 2 lobes. For a d orbital, we have 2 nodal planes, and therefore we get a 4-lobed sort of shape for the d orbital. And the shading here is representing the sign of the wave function, positive or negative. And then for an f orbital, L equal to 3, so we have 3 nodal planes, and we end up with this 6-lobed feature. So we can see that the number of nodal planes is equal to the orbital angular momentum quantum number. Here what I'm plotting is the wave function for a 2px orbital along the x-axis. And so what we can see is far away from the nucleus, the wave function goes to a very small value. And then as we come close to the nucleus, the wave function peaks. And then, because there's a nodal plane perpendicular to the x-axis, it plummets, goes through 0 right at the nucleus, and then the wave function becomes negative. Now, as you probably know, for each principal quantum number, there are 3 different kinds of p orbitals, each with a different value of the magnetic quantum number m sub L, which can take values anywhere from L, which is 1, to minus L, which is minus 1. So we have orbital angular momentum quantum numbers of 1, 0, and minus 1. Each of these orbitals then is the same shape, but a different orientation. So for the 2px orbital, we have a nodal plane perpendicular to the x-axis. For the 2py orbital, we have a nodal plane perpendicular to the y-axis. And for the 2pz orbital, we have a nodal plane perpendicular to the z-axis. If we were to go to the d orbitals, now L equals to 2. So the values of m sub L are the integers between 2 and minus 2. And that means there are 5 different d orbitals. And they have now 2 nodal planes. So we can see for the orbital we're going to call the dxy orbital, you have one nodal plane in the yz plane, and we have another nodal plane in the xz plane. And then 4 of these 5 orbitals basically look the same, just with a different orientation of where those nodal planes lie. And then the 5th d orbital, the dz squared orbital, is slightly different in that it has nodal cones rather than nodal planes. But energetically, it's equivalent to the other 4. All right, so now when we think about the orbital energies in a multi-electron atom, that structure leads to the periodic table, which I show here. And as you know, in the periodic table, we can start over here on the left. These first 2 columns are where we're filling the s orbitals. Then we have this 10 element wide section here in the middle. That's where we're filling the d orbitals. Then over here we have 6 element wide block, which we could call the p block, where we're filling the p orbitals. And then we've kind of cut out of the periodic table these 2 rows, which are 14 elements long. The top one we call the lanthanides, and the bottom one the actinides. And those are where we're filling the f orbitals. Probably you're all familiar with the fact that it is the relative energies of the orbitals that lead to this structure. So let me ask you this question. If we were to compare the energy of, shall we say, an electron in the 4s orbital with an electron in a 3d orbital, which one is going to be at a lower energy? Is it the 4s, or is it the 3d? Is it the same everywhere on the periodic table, or does that order change as we move around the periodic table? Okay, let's take just a minute and ask the question, why does the orbital angular momentum quantum number L impact the energy? Remember, it doesn't if we only have 1 electron in the atom, but it does start to become important when we have more than 1 electron in the atom. And to understand why, let's look at the radial probability function for the 3s, the 3p, and the 3d orbitals in a hydrogen-like atom. If we were to look at the maximum in the radial probability function, we would see that it's farthest from the nucleus for the 3s, and a bit closer to the nucleus for the 3p, and then closer still to the nucleus for the 3d. As we go from s to p to d, as the value of L is increasing, that orbital is shrinking. Right? It's not extending as far from the nucleus, and that has important implications when we talk about bonding. But you would think if the orbital is shrinking and getting closer to the nucleus, it should experience more attraction to the nucleus, and it should be at a lower energy, right? Ultimately, when we talk about the energy of an electron in an orbital, what we're really talking about is its attraction to the nucleus. Well, to understand what's going on, we have to zoom in and look at this region close to the nucleus. And when we do that, and that's shown up here in this inset, we see that because of the radial nodes, the 3s orbital has this peak in electron density that comes here at about 0.2 angstroms, so really quite close to the nucleus. Then we have the 3p wave function, which has 1 radial node, and it does have this peak right here at maybe 0.8, 0.7 angstroms from the nucleus. And so that gives the 3p a non-negligible electron density near the nucleus, but not quite as much as the 3s. And then the 3d orbital, which doesn't have any radial nodes, right? It doesn't have that. So there's not a lot of electron density from the 3d orbital close to the nucleus. And that's the reason why it's at a higher energy than the 3s and the 3p, even though it actually is smaller. It doesn't extend out away from the nucleus as far as the other two. Hopefully, most of what I've said up to this point will really be kind of like a review for you. Okay, next let's look at the energies of specific orbitals. And these values given here are taken from Dirac-Fock calculations of an isolated atom. When we look at the energies of individual orbitals, we see a lot of interesting things that we sometimes don't realize, but help to explain many of the trends we see in the bonding and the properties of the elements. The first thing we see is that as we move up and to the right, over here toward neon, the orbital energies become more and more negative. As you should have learned in general chemistry or physical chemistry, that's because we're increasing the effective nuclear charge. But we see quite a bit more than that. Maybe what we should think about next is the relative energies of the 4s and the 3d orbitals. Right? This is a question I asked you to think about a few slides back. So when we're out here at potassium or calcium, you can see that we have a pretty high energy for the 4s orbitals. There's nothing for the 4p and the 3d because they're empty. So what that tells us is for those elements in the alkali metals and the alkaline earth metals, the 4s orbital must be lower in energy than the 3d orbital. Now, normally your brain would say, okay, well, we fill up the 4s orbitals and now we start to fill the 3d orbitals, which must be higher in energy. But look at scandium and titanium. Already, the energy of the 3d orbitals is lower than the energy of the 4s orbitals. By the time we get to the end of the transition metals, look at zinc, look at gallium. Now we have the 3d orbitals becoming much deeper, much more stable than the 4s orbitals. And of course, what do we know about the chemistry of zinc? We know that zinc in many compounds takes on the +2 oxidation state. It loses its 4s electrons. It does not lose its 3d electrons. You will not encounter a compound where you have zinc 3+ or zinc 4+. So by the time we've reached zinc, the 3d orbitals have basically become core orbitals. And when we go to gallium, now there's a 20 electron volt gap between the 4s and the 3d. And that gap gets even bigger and bigger. By the time we get to krypton, the 3d orbitals are a full 70 electron volts below that of the 4s, right? So they're deep, deep core levels now. And that explains a lot of the chemistry. We can also see a similar trend if we look at the energies of the s and the p orbitals. Let's come up here to boron. The 2s orbitals, which we know should be lower in energy, are about 5 electron volts lower in energy than the 2p orbitals. But that gap keeps getting bigger and bigger, and by the time we get to fluorine, the gap is something like 23 electron volts. And that's going to influence the way these elements bond to other elements. For fluorine, its 2s orbitals are largely core orbitals. They're not really participating in the bonding. But when we go to carbon and boron, that's certainly not true. Now, there's other trends that we might find here, but I do just want to point out one other important trend. And that is if we look at the heavy p block elements, and let's look at the relative energies of the valence shell s and p orbitals. So if we go to something like gallium or germanium, you can see for gallium, the s orbitals are about 6 electron volts lower in energy. For germanium, it's about 8. If we go to indium, we see 5.5. Here for tin, it may be about 7. So those are the kind of relative energies of the s below the p. When we go, though, to thallium, Instead of the s orbital being 5 electron volts below the p orbital, now it's about 7 electron volts. And for lead, we're pushing upwards of 9 electron volts. And we see the same trend for bismuth. So the thing you want to notice here is that when you get to the 6th period, the s orbitals are something like 2 to 3 electron volts more stable than you would predict they're going to be from the trends elsewhere in the periodic table. And the reason for this unusual lowering of the s orbital energies has to do with relativistic effects. Right? Because the nucleus is now so heavy, the electrons, when they're near the nucleus, move at speeds that approach the speed of light. And this is particularly true for the s orbitals because they don't have a node at the nucleus. And that effect has some important implications on the bonding. One of the most obvious ways we might see that is if we were to look at something like the most common oxidation states. So if you were to look, let's say, down group 4A, silicon in most compounds is going to be silicon 4+. Germanium, mostly germanium 4+. You get to tin, usually 4+, like SnO2, but now we start to see the emergence of the 2+ state being stable enough that we can make compounds that have tin 2+. And then once we get to lead, the chemistry of lead is dominated by lead 2+. And you have to go to quite oxidizing conditions to get lead 4+. And the reason for that has to do with the relativistic stabilization of the 6s orbitals on lead, on thallium, on mercury, on bismuth. Size is also important when it comes to orbitals, and size is not a very easy thing to define for an atomic orbital because it doesn't just stop at a certain point. But if we take the maximum of the radial distribution function as a proxy for the size, we can make some comparisons. The main point I want to make here is that every time we fill a subshell for the first time, the electrons in that subshell are unusually small. They experience what you might almost describe as an anomalously large attraction to the nucleus. So what do I mean? If we were to look at the sizes of the 2s and the 2p orbitals as we go across the second period, you can see that by and large they're almost the same. Whereas if we were to go to the third, fourth, fifth period, you can see that the s orbital becomes smaller than the p orbital. Now, the reason why that the 2p orbitals are anomalously small is if we think about the core orbitals, there aren't any p orbitals. The absence of orbitals of the same shape closer to the nucleus means that the p orbitals experience an unusually large attraction to the nucleus, and that makes them anomalously small. And the fact that the s and p orbitals in the second period are almost the same size is why we see a strong prevalence of pi bonding for those elements. Right? Think about the differences in the chemistry of carbon and silicon. Carbon chemistry is dominated by many, many pi bonds. Pi bonds are very rare in silicon chemistry. So you might say the whole chemistry of life depends on this. If we go to the 3D orbitals, you can see that the 3D orbitals are particularly small compared to the s orbitals. You know, the d orbitals are always smaller than the s orbitals, but the difference is most notable for the 3D orbitals. Right? And so that gives the 3D transition metals specific properties. They can have variable oxidation states. Because the d orbitals are somewhat in between valence and core orbitals, we can have unpaired electrons easily. That gives rise to magnetism. Now we see those same kinds of things in the 4D and the 5D orbitals, but they're particularly pronounced for the 3D orbitals. And then if we were going to go down to the lanthanides and the actinides, which are not shown here, you would see that the 4F orbitals are very, very small. And because the 4F orbitals are so small, they are legitimately core orbitals. What does that give us? Well, first of all, we see that the +3 oxidation state is very prevalent for all of the lanthanides. Right? We don't see that kind of constant oxidation state anywhere else really in the periodic table as we move horizontally. It also leads to very sharp electronic transitions between different f orbitals, and that is the basis for many luminescent materials. So when we talk about phosphors and other important luminescent materials, the lanthanides with these partially filled 4f orbitals play a particularly important role.